continue our discussion for today, I will briefly explain about the mathematical method that we use to complete our assignment. Right, so basically there are two problems here, so I will go through each of them one by one. Right, for the first problem here is that the fuel consumption in a moving vehicle. So as stated here, we can conclude that the main equation here is that the distance equation, which is the ST, and then with that in mind, we can continue our first question, is to find velocity and acceleration. So for velocity is the derivative of distance, while acceleration is the derivative of velocity. So with that in mind, we have to differentiate the main equation, which is the ST, to find velocity, and then after we find the velocity, we can find the acceleration. And it is also stated here in the problem to find the after 2 hours. So with that in mind, we can say that T is equals to 2. So we have to substitute 2 inside velocity and acceleration formula. Right, so moving on for the second question, we have to find the rate of fuel consumption. So it is given here that RT is equals to kVT and K is equals to 0.05 liters per kilometer. Right, so why do we use velocity here? So basically velocity determines how many kilometers per hour the car is traveling. And what do we calculate here? We calculate the liters used for each kilometers, which these are represented by K, which is 0.05 liters per kilometer. And then for the third question, we have to sketch a graph. It is stated here that we have to sketch the graph of velocity against time. So with that in mind, we have to use the velocity equation that we got from the previous question. And by referring that, we can conclude that we have to do a quadratic graph. So with that in mind, we can say that the car is not moving when velocity is equals to 0, and the car is the fastest when the acceleration is equals to 0. Right, so for the graph interpretation, we are going to start at x equals to 0 and y 0 until it stops at x equals to 30.33 and y is equals to 0. Alright, so moving on to our second problem, which is the cooling feed efficiency. So first problem, it is quite complicated. So our best approach as a team is to understand the logic behind this rather than just going straight to the mathematical solution. Alright, so with that being said, what is the main logic here? What's the big idea here? So first, by increasing the fin length increases the surface area, which lead to more heat loss. And then next, by increasing length too much causes temperature to drop along the fin. So this means that there is less effective heat transfer. So there is a balanced point where heat dissipation is maximum. So with that logic in mind, we can go to the mathematical solution. So first, it is given here that x is equals to fin length in centimeters, and qx here is equals to u times p, or 120x times to the exponent to the power negative 0.1x. So with that in mind, we have to use the product rule to find the derivative of it. So why do we find the derivative of it? It is to find the turning point or the optimal fin length. And then to find the critical point, we have to say that qx is equals to 0. And after that, our final step is to find the differentiated of qx, or the q double differentiate x, to verify if x is equals to 10 is the maximum point. And then for the next question, it asks us to plot the Desmos graph. So this one is just to verify our answer lah. So my other teammates will go into more details for this part. Right, so that's all from me. Our discussion will be continued by next group member. Right, thank you.
Assalamualaikum, my name is Muhammad Haziq bin Zaimi. I will be presenting our mathematical method used to solve the problem assigned to our group. The first question is question 4.1, which is about fuel consumption in a moving vehicle. For part A, as stated in the question, we are required to determine the velocity and acceleration of the car after 2 hours. To find the velocity, we differentiate the distance function with respect to time, where velocity Vt is equals to ds over dt. The equation was digitally typed and differentiation was performed, resulting in Vt equals to 20t minus 1.5t squared by substituting 3 equal to 2. into the equation, the velocity obtained is 34 km per hour. Next, to find acceleration, we differentiate the velocity function Vt equals to 20t minus 1.5t squared with respect to time. This gives the acceleration function. By substituting t equals to 2 into the acceleration equation, the acceleration obtained is 40 km per hour squared. For part B, we are required to find the rate of change of fuel consumption used for the 2 hours. It is given that the fuel consumption rate Rt is proportional to the velocity of the car. So the relationship can be written as Rt equals to kVt, where k equals to 0.05 liters per kilometer. Next, the velocity of the car is given by the formula Vt equals to 20t minus 1.5t squared. We substitute this velocity function into the fuel consumption equation, resulting in Rt equals to 0.05 times 20t minus 1.5t squared. To find the rate of change of fuel consumption, we differentiate Rt with respect to time. The result represents the rate of change of fuel consumption with respect to time, which equals to 0.7 liter per hour squared.
Hi, I'm Zahir Afifi bin Shamsul, AA250103. For my part, I would like to explain about digital solution step for question number 2, which is cooling fin efficiency. Heat transfer rate of cooling fin is given by Qx equal 120 x exponent to the power of negative 0.1x, where x is the fin length in centimeter. How can we find the optimal fin length x that maximizes heat dissipation? First, we have to differentiate the given equation. Since the equation has more than one function multiplied with, we must use the product rule. By using the product rule, we can find the maximum point where q prime x is equal to 0. Since exponent to the power of negative 0.1x is never 0, we can ignore it and calculate the value in the bracket. Thus, we will obtain the value of x where x is equal to 10. To ensure that x is equal to 10 is the critical point or the maximum point, we can differentiate the equation for the second time by using the product rule as well. After differentiate the q prime x, insert the value of x into the equation. Then the answer will be negative 12 over exponent, which is less than 0. Now, this means that after inserting the value of x, the q prime x will decrease drastically, which proves that the peak point is x equal to 10. So moving on to the next question, which is digital task. We have assigned to plot the qx into the graph by using the Desmos graph.
Assalamualaikum and good morning. My name is Muhammad Ahmadini bin Mustafa, AA251427, and today I will be interpreting a graph about the discussion and conclusion for both graphs. For the first graph, velocity against time. The car accelerates from rest, reach a maximum velocity at 6.67 hours. Then decelerates until it stops at 13.33 hours. Then, upon that, the car will be in reverse direction when velocity is negative. Next is for the second question, which is graph 2. The interpretation is, the graph shows a quantity that initially increases with x until it reaches a maximum point where x is equal to 10. Then, it decreases drastically. This indicates that the system experienced an early build-up followed by dissipation of heat over time, which is typical processes of heat transfer. So that's all for me. Thank you.